So before we begin, I'll take my little poll. Anybody use Pandas here? Okay. Anybody have a love-hate relationship with Pandas? Okay. So for those of you who did not raise your hand, you can leave now. So that was the joke of the day. Okay. Today we're going to talk about the future of Pandas. I'm going to describe what we currently have and then some possible directions where we can go. So before we start, some legalese. We can read that really quickly. So my name is Jeff Reback. I've been maintaining Pandas for about 5 years. I currently work at 2 Sigma. I develop, we'll call it holistic approaches to modeling. Essentially, I think about the interface for modeling and how you can interact with your data in a very Pythonic way. We have lots of data, we write lots of models, and we like to make them easy to do. So you all know this guy. He actually sits in the room sort of next to where I sit, and so he gets all the kudos for Pandas. I get all the complaints. I guess these could be mug shots, I suppose. So yeah. So the what?
He's the victim picture. You're the
Right, exactly. That's good. So we're going to give the state of the Pandas. I'm going to talk about the good, the bad, and the ugly. I originally had, there's a nice Clint Eastwood film by the same name, and I had the nice video, but I had to take it out because of, copyright and all this. So today, we kind of a little bit of a sad Pandas. And I'll go through some reasons for this, and hopefully we can have some happy Pandas in the future. All right, let's talk about the good. So this slide is actually a very interesting take. I'm not saying Pandas did this. That's the next slide. This is the growth of Python. We can't all attribute this to Pandas. I mean, obviously, the machine learning craze, really took off in the early, in 2010, 11 timeframe. And Python has really taken a lot of mind share, and this has brought a lot of folks into the ecosystem and has really proliferated the use cases. And as a result, the software has become increasingly more robust. This is also another recent, this was on Twitter. Pandas now has something like 1% of all Stack Overflow questions. So it begs the question, is Pandas getting more popular, or my theory that there's just more bugs? And as you can see, Pandas actually has nice curve there. This is when I started managing Pandas. Okay. So this is a similar slide to what I drawn a couple of years ago. Pandas is treated almost as a UI or UX to the entire Python ecosystem for data analysis. Pandas is a very large package. It has connectors to lots of things, so it's easy to bring your data in. Wes used to comment that read CSV basically made Pandas accessible to the world, or rather made data accessible to the data scientists, who a few years ago were just called statisticians. So the point is that Pandas is treated as a go-to tool. You're in your IPython prompt or your Jupyter notebook, and the very first thing you import is Pandas to just get your data in. And then, of course, you can, do lots of manipulations and transforms, and you can, then, very easy to graph things. We all love matplotlib, and we all love the associated libraries in the visual ecosystem, but Pandas has a lot of built-in plotting that just works. And, of course, we put the connectors here to the statistics and machine learning libraries, which are, of course, what a lot of folks really want to use nowadays. And Pandas is an integral part of this. I've seen many talks here at PyData, and it's all the 90% preparation to feed into your machine learning model. If you have bad data, you have bad models. So, all right. So I think a lot of folks know what the good things are of Pandas. It makes their life easier. It helps them get their work done. But there's some bad things. So Wes did a post, he did it a while ago, but this is an update of it, I think about a month ago. So I'm not going to actually talk about his actual list. I will mention a number of things on it and give my own take on this. And so these are not all the issues, but some of the issues which people are facing in the current Pandas. So yes, this is a pun. Missing data is a problem. And I'm not going to say that missing data Pandas handles very well. The problem is we don't handle it in a really nice way in certain cases, and I'll show you an example of it in a second. The other two examples up here, so one, this is essentially a dictionary or categorical mapping. This has been a problem. It's a little bit ameliorated in current Pandas, but it's a problem. It's not a first-class data type. And down here at the bottom, this is something that I think a lot of folks would really want. They want units attached to the data types themselves. Now, we have a lot of workarounds and a lot of ways to make this work to some extent, but it's not built in. It's not first class. So here's an example, missing data. I mean, this is the classic, your integer data, when you reindex and introduce missing data, turns into float data. This is unexpected, to say the least. And unfortunately, some of the infrastructure that Pandas is built on was designed 20 years ago. Think about NumPy was designed in the early 2000s, and even that has a prior history to it. Pandas first came to about in around 2008, 2009 timeframe. So we're talking over 10 years ago of our infrastructure. Here's some more issues. We have a fairly complex group by semantics, and I'll show you an example in a second. And we have some issues with copying. And again, I'll show you an example. So when you're actually working with data, this may be an obvious problem where, so we have a random data frame here. A is, we're going to use this as a grouping key and a couple of values. Okay? So this is a standard example of demeaning. You do a group by and apply, so we form the groups. We want to act on the B column, and then we're going to demean. Great. It's actually pretty readable here. And that's one of Pandas' strengths, of course, is that things are readable. Unfortunately, this is very opaque to you. We cannot introspect this lambda. And maybe that's not a problem, except for the fact that when this does not scale well. Okay? This is all actually executed in equivalently of a Python for loop. What you should be doing is this. This is what I could term unwrapping group by. Okay? And it's the same type of transformation. But here's the rub. I don't want you to have to do that. Pandas should be smart enough to figure this out. There's some limitations in the language that does not allow us to easily figure this out. And this is where we're going to move in the future. I referred before to complex group by semantics. So a very common operation, of course, is to group by and then to aggregate potentially different columns to different aggregators and to even rename those. Okay, we actually recently removed this capability because you had to do a dict of dicts. And this could introduce some ambiguity in the syntax. And further note that we're using strings here to define our aggregators. It works, it's fine, but it could be a lot better. Everybody must love this message. I threw this in a couple of years ago, and I threw it in for good reason, too. The problem is I would get so many issues that people would have a data frame and they would assign something to it, and then it wouldn't work. I'm like, what's going on? So it turns out they were assigning to something which was actually a reference to something else, and they were doing the two operations, and it was just gone. So now at least you have a warning. It's not a great warning, but you have a warning. So this is a problem. These 3 points actually do come from Wes's post, but they really boil down to a couple of things. One is Pandas has essentially a bespoke memory layout format that underlies it. And this is the root of a lot of issues, and I'm going to show you that in a second. And two, it's not really designed for modern architectures. It's not really designed to handle multi-core in a nice way. So you end up with this problem. Pandas is great for, we'll call it smaller data sets, 5 gigabytes and less. If you have really large data, you don't use Pandas anyways. You're using Spark or using maybe MPI or using some sort of cluster anyhow. But there's a large midsection of data sizes where Pandas would be very useful. But you need generally a lot of memory to deal with Pandas nowadays. So say, the practical limit is, say, 10 gigabytes for a data set. You roughly need, say, 10 times the amount of memory to manipulate it in a fairly easy way. And this problem only gets worse as you scale. This all stems from the original design of Pandas. So we have this thing called block storage. And here's just a little mini example. Say we have a data frame with 2 data types. We have 2 float columns, and we have 1 integer column. And everybody would guess that really Pandas is holding 3 arrays, 3 one-dimensional arrays. But this is not true. Pandas actually holds this in 2-dimensional NumPy blocks. And they're segregated by data type. And at first you look at this and like, that seems okay. And it is okay for certain applications. So back in 2008, this was great, actually. What would happen is you invariably took a 2-dimensional NumPy array from some aspect of your system, it was all floats, put it in a data frame. That's extremely cheap because we don't do anything with it. It's almost a pointer. And then you could start doing operations. Great. We do actually transpose, so then it's actually memory aligned, so actually aggregations are pretty fast on it. But in 2008, this was probably great. The downside of block storage is this. If you're adding columns, you get a copy. So repeatedly adding things is bad. This is why the standard recommendation is to create everything and then put it in all at once. Furthermore, this introduces these weird copy semantics. If I try to take a column out, I get a view on that column, mostly. But if I then try to modify that, I can get into some very odd situations because we don't own the memory. We're deferring to a NumPy array, and sometimes the semantics are a little bit off. So this is a problem. It's worked well, but it's a problem. So we talked about the good, the bad, and now the ugly. You've probably seen this drawing before. There's been several other talks at this conference about Apache Arrow and the friendliness, or rather the unfriendliness of the various formats. So the basic issue is that I'm increasingly want to use Pandas because I like its API. It's very friendly. But I also want to interact with other systems. Maybe my data is stored somewhere else. Maybe I want to use Pandas in a multi-core way. I want to interact with Spark. Lots of reasons. And the problem is you invariably get to a situation where you're copying and converting and constantly serializing and deserializing data. And this is causing performance issues. In the present iteration of Pandas, and we've been iterating fairly quickly. We try to generally release a major release every 6 or 7 months with minor releases in between. And we've actually had quite an uptake of contributors. I think we have 800 or 900 contributors at this moment. And so there's a lot of folks who really do care about specific edges in Pandas, which is great. So we've made some strides in, we'll call it making things a little bit better for most folks. So example, to ameliorate the ability to store large amounts of non-numeric data, like strings. So we introduced this categorical data type. Now, it's not the best thing in the world. It's not a first-class data type. It's not. It's actually solving 2 problems. It's storing the memory. It's solving the memory problem of storing multiple pieces of data, and it's also acting as a so-called factor. Okay, it's acting as another data type. So we're using things in a little bit loose way here. Recently, we added support for Parquet, to read and write Parquet in a limited way, so people can access a better way of storing their data. And we'll talk about this a little bit later in the talk. And on the multi-core front and the distributed front, there's a tool called Dask, which I'm sure a lot of you are familiar with. This allows you to scale your Pandas and scale NumPy. and scale your computations by parallelizing, either locally across multi-core or across a cluster. So there's hope. But the real hope is essentially a redesign of Pandas. And this is actually a little bit tricky. So here's the slide. And I'm going to talk through this and show you some examples of why this makes sense and why this is a good idea. And I'll give my standard joke. What's the difference between a heart surgeon and a mechanic? They're both doing the same thing, right? They're replacing the guts, but the heart surgeon in case the patient's alive, right? Anyways, I guess it wasn't a great joke. Okay. All right. So I'm going to talk through the stack a little bit. This is the architecture which we feel quite confident will solve a lot of these issues. So primarily we have three components here. At the top, we have a compatibility layer. We're actually going to talk about that last. In the light blue, we're going to talk about IBIS. Okay. And then we're going to talk about Apache Arrow a little bit. So here we go. So what is IBIS? These two layers compare to IBIS. IBIS is a language for talking about what you want to do. It's an expression language. It looks and feels very much like Pandas. It feels very much like deferred Pandas. For those of you who work in a, we'll call it the big data field, if you're familiar with Spark, it feels like that. You have to, or if you've used Dask, you build up an expression, you do a series of operations, and we'll see them in a second, and then you say, do it at the end, or collect, or execute, okay? Or compute, actually, for Dask. This is a very powerful concept of where you're building up your expression, and then you're doing the execution all at once. Okay, Pandas is an eager execution engine. It doesn't do this. Why do we care about IBIS? Or how is it useful? Let me back up a step. This library was actually developed primarily to translate Pandas-like code to run on Impala. Impala is a special form of SQL engine. In fact, it has a very nice property where it allows you to, if you're very explicit about your UDFs, your user-defined functions, in other words, the stuff that goes in the apply, it will actually compile them. Okay, it allows you to have a lot of control and therefore get a lot of extreme performance. It's been extended IBIS has been around a couple of years. It's been extended to actually interact with virtually all SQL platforms. Now, you may be asking, you've probably heard of SQL Alchemy. We actually use SQL Alchemy under the hood to address certain engines like Postgres or SQL Server or SQLite. But we also talk to other engines like BigQuery. We talk to Spark. And the idea here is that you write code, then you can direct where it goes, where it executes. So here's an example. We have a data frame. We talk to it like it's a table, like it's a SQL table. And if you'll notice, it's typed. Everything is typed. And this is the key to the power here. We know a priori all the types. We know the operations on those yield what they yield, what types they yield. So in this case, we have a little a Pandas table. It has a timestamp, it has an int64 column, and it has a string column. Okay. Now, I say execute, I get back a data frame. So far that's not exciting. But what we've just done is we said, hey, I built up an expression. In this case, it's just simply a data frame. It's simply a table. And now I want to get the result. Here's where it becomes interesting. This is a very simple computation. I'm projecting a single column out. I'm selecting the ints column. I'm doing a comparison with 1, and this returns a Boolean result. So if you look here, I don't know if I can do this. No, I'll do it over here. So if you notice, this shows the operations what we're selecting. We're selecting a table column, and it's yielding an int64. Okay? That's the D type of that column. Here, our literal is an int 8. And then when we do the greater than operation, we yield the Boolean. So the point is, we know a priori what the operations are. Sorry, what the data types of the resulting operations are. Well, this doesn't look exciting yet. Let's get a little more exciting. So here we're starting with the same computation on the bottom here. And then what we're doing is we're selecting this out, and then we're doing a reduction. We're doing a sum at the top. Now the reason this is interesting is because I can then take this entire expression and actually evaluate it at the same time. So this allows me to actually, when I'm iterating through this column, to do the filter first and then the sum at the end. Okay? I don't have to do multiple operations and create intermediates and temporaries. I can do it kind of all at once. It allows me to do a lot of optimization under the hood. Here's a more complicated example. This is no seatbelts. Okay. So this is a little more another example of doing a join. I didn't show the actual join table on the right-hand side, but this is at the base the same operation. It has a little bit of the same operation in here. It's a slightly different example. What I wanted to show about this is we have complete control over the syntax here. Now, we're trying to emulate Pandas, and it will come really close. We may even, in fact, make it exactly the same. But there's some key differences, and these are the important points. If you'll notice in this group by expression, I'm using aggregate, but after that, what I'm doing here is I'm doing a key equals value pair. Now, I could actually make this work in Pandas right now, but what I can't make work is the very final point where I say join.value.sum. That is a deferred expression. If I did that in Pandas right now, it would probably work, but I wouldn't get the result I expect. Here, we are giving effectively an instruction to the group I to aggregate according to that column. So I can defer this operation. So basically, IBIS is this. It's a compiler. Takes Python code. Here, this is a little example, and we're going to turn this into SQL code. We're going to take an integer, add 10, multiply by 10.0, and then round it. We end up with an int64. We've gone through a couple of transformations. We're going to compile this and get an actual SQL statement. So in the examples before, I translated the same code, or the same, not the exact code here, but the point is I can take my code and I'm agnostic to my backend. I can translate to Pandas, I can translate to Spark, I can translate to BigQuery, okay? I can even mix these. I could, as an example, have one node which selects from Parquet, another one which selects from a CSV file, and do things with them. It abstracts this away from the user. So we just talked about the IBIS layer. Now I'm going to talk about the Arrow layer. Arrow is just a backend here. It's nothing more complicated or different in theory than like a SQL backend. So Arrow, there's been a couple of talks, as I said, in this conference. Arrow is very fast. It supports zero-copy protocols to and from data frames. It's very flexible, provides messaging, and it's actually widely supported by many developers across many projects. Okay, so this makes us friendly again. And I'm not going to go into too many details. Why does this work? Well, think of the data frame on the top. That's what we like our data. And we're going from traditional row-oriented storage to a columnar format. Columnar format is great for analytics. You get per column D types. You get optional compression on those columns. You can, and much more importantly, you're normally just interested in a certain subset of columns. Okay? Apache Arrow right now they're in a phase where they're working on introducing computation kernels. So this is not just a messaging format. This is an actual computation platform. Now it's not going to be the entirety of Pandas. It will be a general purpose cross-language computational platform. Standard operations like mean and max will be implemented, things like that, casting. And these will be generally useful to Pandas and to other languages as well. Okay? So here's a little example of what you can do once you know about these so-called operator graphs. And IBIS can just construct this and give it to Arrow. So take this little simple computation here. So we're taking a vector a plus b, we're taking the log of that, and then we're doing a reduction of sum. So the idea here is that, and this is completely transparent to the user. This is the nice thing about this. We can do parallelism here. We can do multi-core things. We could do all kinds of crazy stuff, and you don't even know or care. This is a lot like the package that we use currently called numexpr. We can do things like eliminate temporaries, push down. We can do a lot of things here. The point is, it's going to just work, and it'll be transparent to the user. Okay, the one last thing I'm going to talk about here is how do we get there? So up till now, I really only talked about the table abstraction or the array abstraction, a 1D or 2D collection of arrays. Pandas is more than that, actually. It has these nice concepts of indices. It has a row index. It has column labels. This is a little bit odd. SQL does not have these concepts. And so they've proven very useful in Pandas, actually. Indices are, for a lot of situations, are useful, but they can also add some complexity. So the IBIS and arrow layer will be built upon an array and a table abstraction without indices. This compatibility layer will add them back. The goal here, of course, is to make Pandas compatible. It won't be a complete drop-in replacement, but it'll be pretty close. So where are we now? Arrow is a first-class project, has been actively developed, especially over the last year. Its format is pretty stable, and computation kernels are being worked on every day. IBIS is actually a fairly mature project at this point, and we are building additional backends. We had a fellow build the BigQuery backend in 3 days. It was not crazy. Pandas 2 will basically compose these two building blocks with a compatibility layer on top. What can everyone do? Well, we're at the NumFocus conference, which is great. You're supporting NumFocus. Pandas is a NumFocus sponsored project. We'd love for you to contribute. Time or funds. This is a big project. As I said, this is like us, replacing the heart while you're using it. I've always been a big fan of backwards compatibility, and we still will. Things will break. Things will not work as expected, but I think we have a large installed base, and I think this means we have a lot of beta testers out there. Thanks. I'll tweet the slides. They're up here on SlideShare, and then that's my Twitter handle. Any questions?
So most Python libraries I've seen are in Apache. I was just wondering if you knew why Arrow is part of the ASF.
So the question was, why is Arrow part of the ASF? Why is it Apache? I don't know, actually. Apache is a very nice license, actually. It's pretty commonly used. A lot of folks. Pandas is BSD, and probably won't ever change to Apache, unfortunately. So.
It's like the only Python project that I've seen that's
Yeah. Well, I think there's a ton of projects now on Apache, so that are. Yeah, almost all the projects have Python bindings. Spark, as an example, has Python bindings. Beam and Flink and Airflow. Yeah, maybe. Anyways, yeah.
Would you say that the bulk of your work right now is kind of preparing to inject a query plan compiler into Pandas framework?
So this stack is actually being worked on sort of, we'll call it both ends. Wes is diligently working on Arrow along with quite a number of folks. And myself and Phil Cloud, who's another developer, are working on sort of the top level of the stack down. It's kind of what's happening. So we're trying to get both ends at the same time.
Okay. So you gave the example of using a lambda where you do x minus mean of it. And so in the end, you showed dot mean, if I remember correctly, right? I mean, my question really is, will the new pandas let you write these user-defined functions, lambdas, and be be faster, right?
Okay, so the question was, will the new Pandas allow us to write UDFs and be fast as well? And this was exactly my point. The answer is yes. So the point is, you write an IBIS, what happens is we can then introspect the lambdas because everything becomes a deferred expression. So we can actually, and in fact, IBIS right now will today do that rewriting of a unwrapping group by, okay? This is the point. We can do some optimization at each level. In other words, at the top level, query plan level, we can do some optimizations. And then as we push down the stack, Arrow will provide another level of optimization and query planning. Answer your question? Yeah?
One more.
Yeah.
So, what's the plan for user-defined types in Arrow?
So the question was, what are the plan for user-defined types in Arrow? And the answer is they are supported. Arrow is essentially a format which allows arbitrary and custom metadata per type. So you can actually extend it without running over these existing types. Am I out of time?
Sorry, yes, if we can move all the questions to the hallway
Sure.
because we need to move to the next speaker. Thank you.
All right.